Hi, I'm here with Henry Steinhauer, and we're talking about performance stuff. Henry, you are a systems engineer, a performance analyst, a senior performance analyst, and you've been working on systems and looking at performance for how long?
50 years.
50 years.
And I'm starting to understand it now.
I think we've got somebody with a little experience here. So tell our audience about you and just a little bit about what you've been doing all this time in IT.
Well, I graduated in '71 from Miami of Ohio, and it's on all the sports pages. It's always Miami, parentheses, Ohio.
Yeah, right.
It's not in Florida. It's just north of Cincinnati.
Okay.
They still have a very good computer course. At the time, I was in it probably about the third or fourth year it was in existence. And they trained systems analysts at the time. They didn't really want people going into the nuts and bolts of the OS. They were not the typical computer science courses where you talk about compilers and go into all of that area. They were trying to bring it to the next higher up level. Queuing theory was something that was introduced even then. And queuing theory is something that is still mentioned, but not well gone into in looking at systems. And I found that's one of the areas that has been neglected a lot, to understand what does this really mean? Why is my system slow? And what do I need to do to improve it?
You've been involved with CMG for quite some time. And I didn't even realize this until just a couple of years ago. I've spoken at CMG before, and I just found out that it goes back a lot further than the web or client server system. I mean, it's gone back to the 70s, right? So
correct.
I'm wondering, like, what was that like, you know, listening to a performance presentation in the mid to late 70s compared to today?
Well, in the 70s through 80s and through the 90s, it was predominantly dominated by the mainframe environment, because the Fortune 500 companies, they were all on mainframes. Insurance companies, with all of their daily processing of policies and renewals, that was all mainframes. It was back in the day where you actually had the pictures where they talk about computers and they show all these tape drives and the big loop of spinning reels of tape. That was the computer at that time. And to improve performance of your back-end processing, your overnight processing was key, because you had to finish before the prime time started. And simple things like using 2 tape drives for your input and output, so that the previous tape drive could be rewinding, getting ready for the next tape to be put on while you were reading tape number 2 on a different drive. That was a tremendous improvement over just single use. And who would have thought? It was the time when disk allocation was being done by hand, if you can imagine. You actually had to lay out a disk drive in track and cylinder notation and assign, Sally, your allocation is this. And there were no multiple extents to the whole process. You either had it right or you failed.
Wow, we have it so easy today.
We do.
And if you found out that you needed to upgrade your system to another meg of memory, what did that look like?
Normally there was a lot of discussion and debate with it, and there were even IBM system engineers who would bring a megabyte of memory in a suitcase. It was that big. There were multiple frames, whole wardrobe-sized boxes, if you will, that were interconnected by wires to another box, that each one of these had to work together in order for the computer to work.
So I think about today's developer who is developing software on a 2 terabyte drive with how many gigs of RAM, and they're complaining because it takes 2 seconds to do this. We've come a long way. So the topic really today is about how the software development lifecycle kind of, some things have changed, but some things are still the same because there's still, the laws of physics still exist, and some of we can learn from the things in the past to
Sure.
apply today. And I'm just wondering, from somebody who has seen it all, and you're still seeing it today, what's some of the biggest changes that you've seen in the life cycle that affects us as a performance engineer the most?
One of the things is just your usage of data, and one of the concepts is the locality of reference. How near to the data is your processing? We're all familiar with CPUs and the fact that there's a level 1 cache, level 2 cache, level 3, level 4, and then finally real memory. And then after real memory, you then go to solid state disks. There's a time penalty every time you move to another layer of cache.
Right.
And people don't necessarily realize that there's examples of, if you do matrix multiplication in the wrong sequence, instead of going sequentially through memory, you're skipping, because of your array size, you're skipping to a completely different part of memory. Consequently, you're getting cache misses when you do that. If you go in the way in which the compiler has laid out your array, and you go in sequence of it, in memory sequence, then you're 10 times faster of doing that array processing. And it's a very subtle difference, but speed-wise, it's tremendous.
But do you think today's developer, just coming out of school, or somebody who's been developing for 2-3 years, is thinking of that butterfly effect when they're writing code?
No, of course not.
Yeah, so how do we get them to understand that effect? If I change these 3 lines of code, but I'm not thinking in these terms, how wide that path of effect is. In other words, now if everything's in the cloud, every line of code you write is affecting your cloud bill in a real financial way, where we see financial penalties based upon not understanding those fundamentals.
It's a hard question, because we've gotten so far away from the actual machine code to understand what's taking place there. There were options in Cobalt, which is, that has come back up into the forefront of conversation. You mentioned that Microfocus is one of your sponsors, and that Microfocus, part of their product base is Microfocus Cobalt, which runs on many platforms today. There are options that you can do in that compilation of code to say, show me the assembler code, show me the bytecode that is actually going to be done. I did that in the mainframe arena, and was able to better understand how CICS transactions work, so that they can have serial reusability of programs. What does that mean? That means that instead of having to get the program off of the disk again to bring it into memory and execute it, I can bring it in once and then allocate all of the working memory in another subspace, and have this terminal user, use that transaction, while at the same moment another user is using that same transaction, but they have a completely different working set of scratchpad memory, totally independent. They're using the same code, but they're using a different area of memory. I had a really classic example not that many years ago at an insurance company. The developer, the analyst, was using OO concepts, object-oriented concepts, and it was in Java. And when they ran the application, they found out that they didn't have enough compute power in their 4-hour window to get everything finished. It was able to be spread over multiple WebSphere JVM engines. In fact, they had 40 CPU engines devoted to this application running in parallel. But they didn't have enough hours. They needed probably about 8 hours of compute elapsed time for those 40 CPUs.
Wow.
That's a huge compute resource. We looked at what was going on, and the database administrator who was working with me said, it can't be the database. They're doing billions of calls, and each one of them is under a millisecond. Well, light bulb, why are we doing that many calls?
Exactly.
What's going on? So I've been in the industry long enough that I follow the problem wherever it goes, whether it's at the end user's workstation, the network, the front end app server, the middle tier, the database, interfaces to other software as a service apps that are called, API calls, message queue calls. Any of those things can bring an application down to its knees. So you need to look at the entire gamut of that application. This particular process was computing insurance agent payment, part of the premium that he gets a part of it. And his boss gets it, and his boss, and his boss, and his boss, so that it was like 5 layers of payment that was being done. What this person had done in his object-orientedness, and he had been in the industry for a long time. He was a senior analyst. He was getting that agent's data in the innermost loop of the process. So every time he got the agent's data, did the computation, and then went back up 1 layer to figure out who's the next person to be paid against that agent's data. That was tossed out to the Java heap. And now he did database calls to get that data again. He said, it should all be in database memory.
Right.
Why should it be a problem? Your databases are slow. No, he was causing so much garbage collection and garbage thrashing, it could not finish. We had a stalemate for about almost a month where he was dug in. I'm not going to change my code. You have to change your code. We're not going to buy more CPUs. He changed his code, put it outside the loop. It finished in 20 minutes.
One small change like that.
One small change.
And that really is a great segue to the next question, because as you're watching this happen, let's say that this may get exacerbated by load. And somebody says, well, let's find out what it's going to do under load. They bring in someone to do a load test. All right, that person who's doing that would probably work with you to be able to see the 360-degree view of, okay, I'm providing load, I'm providing load generation, and we're monitoring a few things, but you're probably able to see a lot more than just what's coming out of this tool.
True.
And you're able to put together and map together those okay, well, your test results are good. They show me this much, and it shows me that, hey, this transaction time may be taking a long time. And maybe you've looked and seen that, yeah, the databases look to be slow, but you're able to see even further than that into, hey, this needle in the haystack, which is the loop problem,
right,
is the problem. Compare what you see today versus what you may have seen 10 years or 15 or 20 years ago. The types of problems you're having to resolve from those types of tests, has that greatly changed? Was it roughly the same? Is it still, it's your database, it's your code, we don't have enough infrastructure, it's still the same suspects, or is it changing because languages are changing, or because techniques are changing, or because infrastructure is now much cheaper than it was 20 years ago in some, I mean.
That's always been the argument. It is, you know, let's just do a forklift upgrade and replace this stuff with new stuff. And in the old days, it used to be a forklift because it was so heavy, and it literally was, you're going to have an outage for the entire weekend as you swap everything around, and you're lucky if you can get it done over a weekend. Now it's a question of just bringing a new 2U or 8U server and plug it in and switch everything to that IP address instead of this one. But a lot of the issues still are the same. Anytime you go off platform of that particular processing, you're going to be introducing delays. And as we saw in this one example, that even though he was doing all the database calls, there was also a high amount of Java heap reclaiming process going on, garbage collection going on, forced because he was throwing all those objects away. They're now eligible to be reclaimed, and now I'm making a request for more objects, even though they are identical to what I just threw out. The infrastructure does not know it's identical.
Right, right. So getting back to, I guess, explaining to people, we've talked about Grace Hopper in the past,
Yes.
about how she used to explain to people that may not understand how long something takes, or how this affects this other system. And we had talked off camera a little bit about this, but can you mention about that?
I'll just also give a plug for any of the people who are watching this. Search her name, because she has some excellent videos of seeing this woman who started a lot of the industry and brought women into the industry to say, hey, it's not a boys only club. You can be here just as much as anybody else.
Sure.
And she proved that in spades. She's just such a phenomenal speaker. I actually accidentally ran into her at a conference in the 70s. I was in school, and we had a chance to go to an ACM conference. And I had made the statement that there must be thousands of computer languages, and she was behind me and said, no, there's only like 350. I wrote a book about it.
Okay, ears perked up. You have my interest now.
You have my interest. But she was interested in the speed of light, the speed of electricity through wires. How long does it take, distance-wise, to get information from A to B? And she called the engineering part of the Navy and said, I need 1 millisecond of light, of wire speed. Send over a spool. I
can only imagine the person on the other end of the line like, what?
and she went so far down to milliseconds and nanoseconds, microseconds. And she had a 17-inch piece of wire that she then used as handouts to people in her conferences to say, this is how long a particular event is. And right now my mind is blank as to what which value it was, but it was the fact that it was 17 inches long. And one of her admirals was saying, well, why does satellite communication take so long? Well, because you have all these 17-inch pieces going out to the satellite and back.
Yes.
That's why.
That's right.
And the same as what we're talking about with the L1, L2, L3, L4, and then main memory, and then going finally to a solid state disk. You're talking about those distance that the electron has to travel to convey information from point A to point B. And we're still in that process. When we look at the internet, you know, I bring up a laptop and go to the web, and I'm going to a particular site that only has one server behind it, I'm still talking about what is the distance here. One of the rules of thumb I'd used for years was 1 millisecond is roughly 100 miles of internet space. And I don't think the numbers are quite as exact now, but it's still very close. And even though we're using fiber between major hubs, coming out of that hub, you're still, some places you can have fiber to your house, one gig internet to your house, or 10 gig internet to your house. But from that point, it's then going over copper to your computer system. I just, last week, was doing a test with a utility called iPerf3, which you may be familiar with that.
Yes.
And it's one of those cases that you use to say, let's verify. One of the questions is, what is our real throughput between this computer system in this location and this computer system in another location? And you can use all sorts of other, ways to try and the vendor says we have this WAN link, it's a 100 megabit or 500 megabit. Yeah, but how much, when we really use it, what do we see?
Right.
So iPerf3 is a very simple utility available in Windows and Linux, or any of the flavor of the Unix environments. And you can set it up, one on a client and one on a server, and say, go for it. I just found out recently one of the parameters is a window size. Window sizes. Who would have thought? But when your TCP window is full, you're not transmitting anything more until you get an ACK back. In one test with this default window, we were getting 3 megabits. When I bumped that window size to an absurd value, suddenly we were getting 300 megabits. Surprise. Who would have thought? In this day and age, I'd have to worry about that.
That's right. But it's still there. And so there's a lot of things that I think people who are still maybe in school, in college, in technical school, and they're learning how to develop, they're learning how to build applications, I think there's still some fundamental things that they may be missing. Maybe they're going too fast through these courses, or maybe, I think there's another level of education that needs to be there that I feel is missing. That's what I've kind of come to the conclusion doing this performance tour and talking to many people, is there's still a level of education in this realm of understanding performance and how things work that just, it's not there, that needs to be there. Would you agree?
Definitely agree. Now, you had mentioned CMG, and I was a regional chairman of the Chicago regional group. We called it the Midwest Computer Measurement Group. And because of a friend who challenged me to pick up the reins of it, I was the chairman from 1980 through 2002. And it was a standing joke. No one really wanted the job, but we did have an election every year. So we would say, who would like to be the chairman? No one. All right, well, be sure to vote early and often.
Right.
Because we are in Chicago.
Right.
And I had a beautiful board, and one of the people was from the Illinois Bell Company, and the hotel that we were using for this conference, Illinois Bell, used a lot of their facilities. So we always got a really good rate for using that hotel.
Right. That's great.
But we would have meetings 4 times a year, and vendors would come, and the things technicians and the people in the industry hate is when a salesperson comes in and they're just doing a blanket sales pitch. And I would always say, time out. All right, you've heard him describe the problem. How many of you had the problem that he's talking about? Maybe one hand would go up. I said, the reason I invited you here was I wanted to know about this process. And we had talked about it before, so hopefully you're prepared. Let's toss out your canned PowerPoint process and let's talk about this part of your product that solves these types of problems.
The solution.
The solutions.
Right.
And that was always a lot of fun. And one of the areas of interest that if people want to explore is an area called queuing theory. Now, the systems of today are built of queuing systems, multiple queuing systems tied together. They're not just one queuing problem. In the old days, one of our first computing queuing systems to analyze would be a gas station. How many pumps do you need to satisfy the flow? How long does it take for someone to pump gas? How long does it take to, pull in, pump your gas, and get out? what is the arrival rate that you see? And we've all experienced the art now of queues from the bank teller, where you come into one queue and you have 4 different tellers. You come into a bank queue where you have 4 tellers, but you have 1 line. Mm-hmm. And you stand here until someone else is ready for you. The kids may not remember it, their parents may, mm-hmm. their grandparents for sure. Mm-hmm. You used to go into the bank and you made a choice. Which teller line do I want to go into? And you went into Sally's line because you knew her and she always gave you a smile. You didn't go into the other lines. Now we go into one universal line, mm-hmm. and now we're served by all of these people. That's a queuing system. Mm-hmm. Queue means line, mm-hmm. British term.
Right.
And if people understood the queuing processes of when I make a transaction, where does it go to? Where does it go to next? Where does it go to next? What are all of the interconnections that have to work properly for this to be completed? Who else is competing for service at node number 2, deep into the stream? Are you isolated, or is that node being shared by everybody else? Those are the challenges that we have today. The visibility and observability of what else is going on. One of the challenges that I've seen in the industry for years is being able to understand and follow a transaction from all of those different points. How mm-hmm. do you tie them together when the call that is made from the app server to a database server has nothing embedded within that call to say this is based on transaction XYZ? Mm-hmm. Mm-hmm. Nothing's in that call to differentiate that, because that query call could be done by 15 different transactions or 100 different transactions. Mm-hmm. What makes this one unique that we need to identify why this is behaving? That's where tools like, and I'll mention a few, New Relic and App Dynamics, both of those are able to capture the SQL that's being done from the Java code from in the app server to the database server. Mm-hmm. And they can attribute that SQL to that particular transaction.
Right.
But they can't, if you're doing a stored procedure call, they don't know where that's going next. Mm-hmm. And now that's a challenge.
And how does it get there, and then what's to tell me how long it stays in this particular place before it goes to another place, and why did it stay there that long?
Exactly.
Right.
Those are the challenges we have still ahead of us.
Do you think that's where open telemetry and open tracing and some of these new initiatives, where, especially like when they're dealing with Kubernetes-based, container-based applications, we're dealing with things that exist now that may not exist in an hour. As they spin up and spin down containers, uh-huh. This tracing keeps track of where it goes and reports back at each segment of the queue. But do you think that may not be the total answer, but does it help?
It all helps. The question is, does it maintain enough intelligence of the identification of that transaction so that you can associate it with what the call before it got to this call mm-hmm. is related to? That's your challenge.
And the biggest challenge for these vendors, like you mentioned, is then how do I visualize that in a way that it makes sense to people so they can quickly identify the problem, quickly drill down, and get to time to resolution.
Correct. Correct.
So still challenges out there. Henry, thank you so much for being on the performance tour. It's been great.